In this section, we will have a look at techniques for modeling thin and slender geometries. In some cases, you might have features that has a thickness that is thin compared to the general size of the model, such as thin films or layers of electrolytes and thin conductors. In those cases, it might be efficient to assume that you have a constant current density in the thickness so that you don't need to measure the electrolyte thickness. And thus the equation for the current density in 3D becomes a surface current density, and the electrolyte thickness becomes a variable that can be spatially dependent. Thin electrolyte layers can be modeled with the current distribution shell interface, such as moisture on surfaces in atmospheric corrosion, or thin electrolyte layers in electrodeposition. And thin metal structures can be modeled with electrode shell interface, such as pipes, metal sheets, and electric conductors on a circuit board. In the case you have a thin resistive or an insulating layer embedded in an electrolyte, this can be modeled with a thin electrolyte layer feature inside the current density interfaces that we have. And it's also possible to model thin metal surfaces without internal loss with the thin electrode feature. And I will show a demo of this later on. For edges or edge electrodes, we have possibilities to model things such as cylinders and pipelines and so on. And in general, in finite elements, edges as current sources gives you a singular potential along the edge. So they are not suited for directly use as potential dependent current source, such as what we need in the corrosion simulations. So for these edge electrodes, COMSOL inserts additional integration points to give a virtual surface area of the anode. And this is shown in red here on the figure on the right side. This improves the efficiency at a small cost of accuracy compared to a solid cylinder. So you will have a much fewer elements, but a few more integration points along this surface. And the main rule is that the mesh must be at the same size as the anode diameter, but this is something that you can vary and see how much you need compared to the accuracy that you need. And this can be used to model long cylinders, pipelines, anodes, and connections between different devices in the electrolyte. Edge electrodes also interact with the surrounding electrolyte through the electrode reactions, and it models the current balance inside the electrode to account for the internal loss inside long electrodes, such as for pipeline, for example. You can model the internal voltage drop that you get along the pipeline. And now I will demonstrate thin layers and edge electrodes. So let's go to COMSOL. And let's just have a look at one of the models for atmospheric corrosion first. So we can look at this atmospheric corrosion busbar. Open that file. And we can have a look at this, how this is built. So if you look at this, you see that you have current distribution inside all the domains. But these are set as current conductors. So inside here you have phi s, which is the solid potential, as your dependent variable. So you have electric ground on this place and some electronic current flowing in, 100 amps. And then you have the electrode current density, which is coupled from this current distribution shell interface. So here in this current distribution shell interface, we model the electrolyte and the electrolyte film, which is a thickness and a conductivity. And then we have electrode surfaces for the different parts. So here we have the aluminum surfaces. So this is aluminum dissolution, and this is the oxygen reduction. And then we have the copper parts, and then we have the zinc plated part here. And then we assume that there is a solid current flowing inside the busbar, and there are currents flowing in a thin electrolyte film with this. So this just adds to the contribution on the top of the surfaces. So this is very useful in case you have a panel, for example, with a metal or a coated metal with a scribe in it, and you assume that there is a constant layer of thin layer of electrolytes lying on top of that. So that's one way of using this current distribution shell interface. I will show some other features. So let's go to the model wizard and make a 3D model. And then I can select corrosion, no, not the corrosion, secondary. We'll go with the cathodic protection interface. And that's the same as the secondary current distribution interface, but it also has some more boundary conditions available. So I click study, and we will do with stationary here. So what I want to do here now is to make a cube. So I'm just making a 1 by 1 meter block. And in the middle of this, I want to put a thin plate, which is insulating. So that should be x at 0.5 meters. So that's in the middle. And here I want to go to sketch mode and just draw a small cylinder, a small circle, I mean. And then we have a square on the outside, and we can do a Boolean operation in this difference. I make a hole in it. So now we have the model here with this layer, thin layer with a hole. So when we go on and mesh this, you can see that you have a uniform mesh all the way. And if you were to model, say that this was a very thin plate, say 1 millimeter acrylic plate or something like that sitting in the middle of this, then you would have very small elements inside this and on the outside of the thin plate. And by using this thin layer functionality, it's easier to save a lot of elements. So I'm just adding a blank material here with some kind of sigma, and then we can just put on a potential here, 0 volts, and then we can put on a current density on this side, so 5 amps per square meter. So we just model a current density that flows through. So let's compute the initial solution. So here we can see that the voltage drop is uniform along the length of the model. So nothing has happened, and this is just a surface that has continuity on it. But if we want to insert, for example, a thin electrolyte layer here, you can put it to be insulating, or you can set a resistance. So it's a thickness and a conductivity. So this can be a thin layer of some conductive material, or it can be a total insulator. And now if we compute again, you can see that you get this voltage drop that only occurs in this hole. And you have a discontinuity in the voltage between the two different compartments. So that's the way to model these things. And you can typically use it to model shields in a tank, or if you have a pipeline that is shielded by some acrylic or something close to your termination points of the pipeline. You can use this to make the modeling easier and more efficient. And then we also have a thin electrode surface where you can model an electrode. So say that this is a thin metal sheet. You can also select if it's on both sides or on the upside and the downside. So that means that you can say that it's aluminum on one side and it's covered with paint on the other side, for instance, and so on. And it's also, we also have a feature for perforated electrode surfaces. So you have a thin layer with a lot of holes in it. So that was this thin electrolyte layer functionality, and you also have the same type of functionality for the electrode phase. So you have a thin electrode layer here. So if you have a metal with a thin sheet of other metal or something with a different conductivity inside it. So that's the thin layer functionality. And it's also possible to use this edge electrodes. So I will show how to do that. In the application library, we actually have a modeling multiple oil platforms that's with edge electrodes and also with the boundary elements functionality. We also have a pipeline corrosion protection impressed current that uses these edge electrodes, so you can see how they can be used on a pipeline scenario. So I will just make a simple model here. So let's go to 3D, cathodic protection. And let's start with stationary study. This. So now I can just create a block. Say it's 100 meters, 20 and 20. And then it's minus 10, minus 10. So here we have a long electrolyte volume, and inside I will put polygon. So it's going to start with, and then 100. So this is my pipeline. And then I'm going to add a couple of anodes on this. So I add another polygon. It should be 4 meters, 1 meter, 0, 6, 1, 0. So there I made one anode, and then I can create another anode by just using an array of these. So that should be 5 anodes, displacement 20, like this. Yeah, so now we've done that, and I can add a material. Like seawater, and we can add this edge functionality. So here we have edge electrode, and you can put that on the whole thing, specify the radius. So maybe that's 20 centimeters. We have our conductivity inside, so maybe 10 to the power of 6 Siemens per meter. And we can type in the equilibrium potential, minus 0.6 volts, and a small current density, 10 to the power of minus 3, maybe. And another thing that we need to remember now is that we're calculating the electric potential here. So we need to put an electric ground at the points. So I'm putting electric ground here. And then we can use either sacrificial anodes, sacrificial edge anodes, or edge electrodes. The sacrificial edge anode, it doesn't make any changes when you use it in a stationary study, but for a transient study, you can see how they change their radius over time as they are consumed. But in this case, we will just do a stationary study, and we assume that they are all grounded, so all are connected to this point, and we have this electrode reaction minus 105 equal to. Okay, so let's just compute this and see. So by doing this, you can actually model very long pipelines and terminations of those, and how they are connected with other structures and so on. So we can see the electrode potentials here, and we can see that everything seems pretty well protected. If we increase the current density here by a factor of 10, we will see a bit more change in the simulation.